I did assign a lot of chapter 6 homework. In fact, I assigned all the problems. So there are different ways you can memorize it. One is by just doing a lot of problems, repetition. But I assigned all of them. You know, if you're having trouble memorizing them, then the more you use it, the easier it is to remember. And so that's the reason I assigned it. But if you already have it memorized, then it starts to become tedious because you already know it. And so if you don't complete that, that's okay. I'm just going to assume that you have them already memorized. The reason I did that was, you know, you might be struggling to memorize them. So, you know, rather than struggle to memorize it, you might just do all the problems. By the time you finish that assignment, then you'll see it quite a lot. And a lot of the problems are repetitious, so you'll get a lot of practice. So chapter 6 is a huge homework assignment, and it's worth doing if you're not memorizing it, or if you're struggling to memorize it. We're going to move on, though. It's time to move on to chapter 7. So let's take a look at chapter 7. So when we look at chapter 7 is chemical formula relationships. The chemical formula tells us the composition. So the composition of water, we can just get from the formula of water. The formula of water is H2O. But it tells us a certain type of composition. It tells us the atom, 2 hydrogen atoms for every oxygen atom. And so in this chapter, we're going to be looking at that. So here, the number of atoms in a formula. Well, the number of atoms in a formula, you just look at the formula and it tells you how many atoms there are. So it's pretty straightforward. 7.2, we're going to look at how much it weighs, molecular mass and formula mass. You know, not everything forms molecules. And so if it doesn't form a molecule, we'll call it, rather than molecular mass, we'll call it formula mass. But formula mass is just a generic term used for everything. And so how much does an H2O weigh? You know, an H2O weighs, and we look, what's the average oxygen weigh? The average oxygen weighs 16 U. The average hydrogen weighs about 1 U, so the average water molecule weighs about 18 U. You know, if we're looking at the average, we'd say, okay, the average weighs about 18 U, but if you pick one molecule of water, you might get a water molecule that's quite a bit heavier than the average. Or you might get a water molecule that's slightly lighter than the average. You know, it depends. Then we're going to look at the mole concept, molar mass, conversions, mass relationships, empirical formula, and molecular formula. And so those are the types of things. So the number of atoms in a formula. So MgCl2, what would you name MgCl2? Is magnesium a fixed charge or variable charge ion? Fixed. And the charge on magnesium is fixed at +2. So we don't have to call it magnesium Roman numeral 2. So this would just be magnesium dichloride. Is that correct? No. Because we don't need di. Because if magnesium +2, we know the chloride is what? -1, then we can figure out the ratio. And so we don't have to be told the ratio. So that's just called magnesium chloride. 2 words, magnesium chloride. What's this called? Well, first off, what's Ba? Bearing. Is that fixed charge or variable charge? Fixed, and what's the charge? 2 plus. In fact, magnesium and barium are in the same family. The family's called what's that family called? Yeah, the alkaline earth metals. What's IO3 charge? IO3 must be, I can tell what the charge is based on this. If barium is plus 2, then that means each IO3 must be minus 1. So what is IO3 minus 1 called? Iodine trioxide. When we use that, we're naming molecular compounds. So if we use iodine trioxide, it has to be neutral. So if it were IO3 with no charge, I would call that iodine trioxide. But this is an ion with a charge, so we can't use that. That naming system only applies to binary compounds. Compounds are going to be neutral. This is binary, but this is a binary ion. And so we have to name that using a different set of rules. So what would IO3 minus be called? It's not called iodine trioxide. It's called, what is it? We have, I'll give you 3 choices. 3 basic choices. It could be called iodide. Do you think it's iodide? With a D? Iodide. No. Iodide's monatomic. This is a polyatomic. It's a polyatomic oxyanide. So it's either an 8 or an ite. What do you think this is? Iodate or iodite? This is iodate. There, you either memorize it, or you know the pattern on the periodic table. And so the name of this compound is barium diiodate. No di. This would just be barium iodate. And so when we look at magnesium chloride, how many magnesium atoms are there? How many chloride? So this one is a level harder. How many bariums? How many iodines? How many oxygens? Yeah, okay, so you got it. That's good. When you look at this, this is carbon, this oxygen, oxygen. What's this called? This one's called carbon dioxide. It's called carbon dioxide. We need the di there because there's another carbon oxide. What is it? Carbon monoxide. So we don't know, is carbon plus 2 as in carbon monoxide, or is carbon plus 4 as in carbon dioxide? We don't know which one it is unless we're told. If we're told it's carbon 4 oxide, then we know it's CO2. And so in this case, we have to use that other naming system here. But how much does a carbon dioxide weigh? Well, we get this, the carbon weighs 12.01 U, that's the black one, and the oxygen weighs 16.00 U. That's called the atomic mass. The atomic mass, is that an average, or is that the mass of an individual atom? Is it the average or the mass of an individual? Well, it's tricky because maybe it's poorly worded. In other words, do you know the 2 isotopes of carbon? There's carbon-12, which weighs exactly how much? There's carbon-12, and it weighs exactly 12 U. Right? That's our standard. And can this be carbon-12? No, because carbon-12 weighs exactly 12 U. This weighs 12.01 U. Well, there's another isotope of carbon naturally occurring, which is carbon-13. Carbon-13 is going to weigh about how much? not exactly, but about 13U. Could this be carbon 13? No, so this must be the rare carbon 14 isotope. It's rare because it's radioactive. Is this carbon 14? No, it can't be. And so what is that? Mass. It's 1201.
Didn't that be calculated mass?
Yeah, that's the calculated, what? Not the calculated mass, calculated. It is calculated. It's the calculated average mass. And it's a weighted average. It turns out that it's, I can tell it's 99% carbon 12 and 1% carbon 13 because it's 99% closer to 12 than it is to 13. Do you see that? 1201. If this were 12.99, then I'd say it's 99% carbon 13, 1% carbon 12. That. And so this is the average. There are 3 isotopes of oxygen: oxygen 16, oxygen 17, oxygen 18. Is this oxygen 16? No, it turns out it's the average because oxygen 16 doesn't weigh exactly 16 U. Oxygen 16 weighs 15.994 U. Oxygen 16 weighs 15.994 U, but this oxygen is weighing at 16, which tells me that this is the average. And so where do I get the average atomic masses of all the isotopes? I get it off the periodic table. So let's take a look at the periodic table. Is it still on up here? Well, this would be the average. Average, this is called the atomic mass, but that's the average of all 3 isotopes. You see it's very close to 16, therefore oxygen 16 is the most abundant. And then we look at carbon. 12.011 is what they have here. The 4 sig figs would be 12.01. So we use the average, and then we get the average. The average CO2 weighs how much? We'll add them all up, we get 44.01 U. So that would be the average mass of the CO2. 44.01. The reason we look at the average is because normally we look at log molecules. A lot. So it's rare that we work with just a single. Let's say I had a billion CO2s. If I had a billion CO2s, I'd probably just want to know the average mass of the CO2. But if I went into, let's say I had a sample of a billion CO2s and I picked one CO2 molecule out of there. If I pick one CO2 molecule, then I don't want the average. If we're only working with one molecule, then I need to know how much it weighs. And so if, let's say, you had oxygen 18 and carbon 13, then the weight is going to be totally wrong. And so if you pick one molecule out of there, you need to know what isotopes it's made out of so we can get the mass of that CO2. It's going to be a lot heavier than this. Does that make sense? So when we're working with a lot of molecules and a lot of atoms, the average is best. When we're working with individual atoms and individual molecules, we don't want the average. We want to know what the individual is. And so if you had a billion people, you might want to know what is the average weight rather than going through and looking individually what their weight is. That would just be a lot of work. And same thing for us. And so we can get these things here. Like, for example, the mass of ammonium nitrate. What is it? Actually, I shouldn't tell you. You should tell me. What's the formula for ammonium nitrate? So ammonium, what's ammonium? NH4, the charge? Plus. And so this is just straight memorization. NH4 plus is ammonium. What's the formula for nitrate? NO3 minus, oh good. That's good. That's fast. It took me a while to get ammonium and nitrate. And so this is +1, that's -1, so 1-to-1 ratio seems best. So this would be ammonium nitrate. CO2 forms molecules. Molecules are discrete unit entities. And so I can have a lot of CO2. If I have a lot of CO2, I have a lot of molecules. Ammonium nitrate is what we call an ionic compound. It's made up of ions. CO2 is what we call a molecular compound. Ammonium nitrate does not form molecules. When I look at ammonium nitrate, it looks like this. Can you tell which one's ammonium and which one's nitrate?
Yes. Yeah, the ammonia is the one with the white.
This ammonium, yeah, and this would be nitrate. With ions, it's like this. You think if you have a positive marble like that, what does Coulomb's law say? Coulomb's law says that unlike charges attract. So if this is positive, then I could have a negative here. But the situation is, if this is positive, it actually wants to surround itself with as many negatives as possible. Do you think a positive is going to come in here? No. In fact, what's going to happen is if this is positive, then another negative is going to come in here like this. But there's even more room over here, so we'll put in another negative here and then another negative here. So which negative is this positive paired with? All of them, actually. And if this were negative, it wants to surround itself with as many positives as possible. That's to maximize what we call the Coulombic attraction. So, if you're like a magnet, then you're going if this is the north pole of a magnet, then the south pole of these four magnets are going to be attracted to it. And so what happens is we build this up, this structure. Do you know what this structure is called? This is a lattice. We call this an ionic lattice. Ionic lattices are going to be represented by the simplest ratio. And in this case, the simplest ratio is 1-to-1. For every positive, I have a negative. It's 1-to-1. The same thing here. This is called a lattice. This is a lattice in 2 dimensions, but in 3 dimensions, it just go up. And the simplest ratio here is for every ammonium, I'm going to have 1 nitrate, but it's actually surrounded by more. Like in this case, the shape of this is going to differ. The shape of the lattice differs because of the shape. If these are just marble balls, then this is what it's going to look like. But these are going to have different shapes to it, and so it depends on how you can pack these together most efficiently. But this ammonium belongs to this nitrate, or this nitrate belongs to this ammonium, or is it this one? Or can you tell? Can you tell which nitrate belongs to that ammonium? You can't because it's not a discrete unit. Either one, it doesn't matter. They're both the same. And so the same thing here. This is what we call for example, NaCl. The sodiums are the positive, the chlorides are the negative. And so when I look at it, I'll just pick the simplest unit. So pick any of these sodiums. So for example, if I pick this sodium, I might pair it with this chloride, or I might pair it with that chloride, or that one. There's no discrete unit because that sodium can be paired with any of these. But the simplest unit will be this. The simplest unit we call the empirical unit, or empirical formula. And so we don't say sodium chloride molecule. That would be wrong because a molecule indicates that we should have a discrete standalone unit. And so a lattice of this should be made up of those discrete molecules. It's not. So we have to come up with another name So rather than saying sodium chloride molecule, we say sodium chloride formula unit. And so a formula unit of sodium chloride would be just one sodium, one chloride. Now the formula unit can be used for anything. And so if I have something like H2O, H2O forms discrete molecules. Here. And so I can say H2O molecule, or I could say H2O formula unit. The same thing. A formula unit of H2O would just be H2O. However, I can't do the same with sodium chloride. I could say sodium chloride formula unit, but I wouldn't be able to say sodium chloride molecule because there's no molecule there in that lattice. Same thing here. So how much does a formula unit of sodium chloride weigh? Well, we can calculate that. We just take the mass, the average mass of the sodium, which we get off the periodic table, which is 22.99. And the average mass of a chlorine, which is 35.45 off the periodic table. And then we can calculate the mass of just one of those units. How much does a formula unit or a molecule of H2O weigh? Well, oxygen's average is 16, hydrogen's 1, so about 18 for that. We can go more, 6 figs. For ammonium nitrate, how much does a formula unit of ammonium nitrate weigh? And so there are some average masses off the periodic table that are very useful to know. And these ones I recommend memorizing, but it's not so critical. You need to memorize it to save time in calculations. That way you don't have to look it up. Hydrogen, the average mass is 1.01 or 1.008. This would be U per atom. Carbon would be 12.01 U per atom. Nitrogen would be 14.01 U per atom. Oxygen would be 16.00 U per atom. These are probably the 4 most important ones to know. So why do we have 2 for hydrogen? We have 2 for hydrogen because it deals with decimal places and 6 figs. So for example, if we only need 2 decimal places, then we use this one. This has 2 decimal places. Here, if we're interested in 6 figs, this one would have 4 6 figs. And so it depends on what we're calculating. So for example, water, I can get the average mass of water molecule quickly. Water has a composition H2O. There are 2 hydrogen atoms, 1 oxygen. We have 2 hydrogen atoms, 1 oxygen. Each hydrogen is, I could do 101 U per atom. This is going to give me 202 U. I have 1 oxygen atom, and that 1 oxygen atom has an average mass of 16.00 U. This is going to be 16.00 U. So in this case, for hydrogen, I want 2 decimal places, because when I add these up, I'm allowed 2 decimal places. I'm going to get 18.02 U. This would be the average mass of a water molecule. And so I get 18.02 U per water molecule. That's 4 sig figs. Typically, we want 4 sig figs. But let's say I'm looking at H2 or H. If I'm looking at H2, then if I have 2 choices. I could do 2 times 101, which gives me 202. 202, that's 3 sig figs. Or I could do 2 times 1008, which is going to give me 2.016. I want this one. And so if I'm looking at H2, the average H2 molecule weighs 2.016 to 4 sig figs. But it's okay that I did it here as 202 because when I add these two together, I'm still going to get 466. And so this is just to maintain 468. So sometimes I'll use this, sometimes I'll use this one. Okay, so for ammonium nitrate, we need to figure out how many atoms are in a molecule of ammonium nitrate or a formula unit of ammonium nitrate. How should I phrase that? If I want to determine the mass, is that going to be a mass of a molecule of ammonium nitrate or the mass of a formula unit of ammonium nitrate, or either one's fine? If I want the mass of water, this is the mass of a molecule of water, but it's also the mass of a formula unit of water. And so this is both the molecular mass and the formula mass of water. That's both. For ammonium nitrate, would it be both the molecular mass and the formula mass, or just the formula mass? Just the formula mass. And so this is wrong. And this is a little bit deceptive because in active example 7-2, ammonium nitrate does not form molecules. So let's get rid of molecular mass. All we can get for ammonium nitrate is the formula mass. How much does one of these units weigh? One of the units contains one ammonium ion and one nitrate ion. So how much does that unit weigh? So ammonium. Actually, did I already ask you what the formula is?
Yeah.
All right. And so we have NH4NO3. That's ammonium nitrate. And so how much does it weigh? Well, we know that this is going to be a molecule or a formula unit or both. Yeah, this is only a formula unit. And so what we're calculating is the formula mass. There's no such thing as a molecule of ammonium nitrate. And so in one formula unit of ammonium nitrate, how many nitrogen atoms are there? There are 2 nitrogens. And if you've memorized it, the average mass of nitrogen to 4 sig figs is 1401, which is going to give us 2802 U. Is U per atom. How many hydrogens are there? There are 4 hydrogens. And so for hydrogen, I'm going to go 4 times 101, which is going to give me 4.04 U's worth of hydrogen. I'm not going to do 108. You know why? It's not going to make any difference because when I add these, I'm only allowed 2 decimal places at the end. So that's why I'm going to use this one. And then how many oxygens do I have? 3 oxygens, and the average mass of oxygen is 1600 U, which is going to give me 48.00 U. So this is going to total out to 80.06 U. That's equal to the formula mass of ammonium nitrate. And there's no such thing as molecular mass of ammonium nitrate.
So ammonium nitrate atoms are not chemically bonded together at all?
No, they're like the marbles. They're odd-shaped marbles. If all the marbles are round, then we can pack them together. But these are packed together, but they're odd-shaped. But what's holding them together is just electrical attraction, like that. And so in that sense, they are not bonded to each other to form a molecule. But in another sense, they're bonded to one another by the electrical attractions, Coulombic force. There.
Would there ever be a time when we would get a different mass for each one of those?
Different mass for each one of what?
The formula of the molecule.
Molecular? Yeah.
In one case, it's that, I think.
Well, it depends on what type of formula you're looking at. In general, actually, let me take it. As long as we say formula and molecular, then they're the same thing. But sometimes we have different kinds of formulas. So do you recognize this?
Hydrogen peroxide.
This is a hydrogen peroxide. And so a molecule of hydrogen, this forms molecules, by the way. A molecule of hydrogen peroxide looks like this. And so this is called the molecular formula. We're going to come back to this. And so in this case, the formula mass and the molecular mass are the same thing, correct? Same thing. So how much does a molecule this weighs? That's 16 plus 16 is 32 plus 2 is 34. So this weighs about 34 U. I'm only going to do the two sig figs, 34 U. But we have something called the empirical formula. And there are two definitions for empirical. The first definition for empirical is by observation, from observation. What was the second definition of empirical? The simplest. And so if we look at the empirical formula, here, the empirical formula is not H2O2. That's not the simplest ratio. The simplest ratio is H1O1. We'll just call it HO. H1O1, HO. And so here's what's the formula mass of this? The formula mass for this is 16 plus 1 is 17U. And so the empirical formula of hydrogen peroxide is HO. Is this the same as the molecular formula for hydrogen peroxide? No. In fact, this isn't even a molecule. We have to take this molecule and chop it in half. If you chop that molecule in half, then we'll get the empirical unit. And so it's a tricky, but this is a case where the formula mass is different than the molecular mass because we're looking at a different type of formula, the empirical formula for hydrogen peroxide versus the molecular formula for hydrogen peroxide. But, I was tempted to say yes, always, because, the other way you could read this is yes, always. This is not a molecule, therefore there is no molecular mass. And therefore, the formula mass and the molecular mass are the same thing because there's no such thing as molecular mass for this. Because you can't have half a molecule. That half a molecule would be very unstable. You call it a free radical and then want to react with something.
You keep using U. Is that just stand for units?
No, U stands for atomic mass unit. AMU. It's just the abbreviation for AMU.
What does the last this formula, and then I can't read the whole thing between that and then 17.
Formula mass about 17U. So this is the molecular formula for hydrogen peroxide. This is the empirical formula for hydrogen peroxide, and they have different masses. So the average mass of a formula unit, in other words, the formula mass of ammonium nitrate is 8.06 atomic mass units per formula unit. Okay. You know what ammonium nitrate is used for? Fertilizer. Yeah. Ammonium nitrate is a good fertilizer because it has lots of nitrogen in there. 2 atoms of nitrogen per formula unit. And this is one way to get nitrogen in the soil. But when I look at ammonium nitrate, I think that doesn't look so stable. Can you see and look at it and say that's an unstable combination? Like, let me give you a stable combination. A stable combination is if I take some cesium and rubidium. If I take cesium and rubidium, I'm going to mix them together, it's fine. I don't expect any trouble. But if I take cesium and react it with fluorine, that's not fine. I expect trouble. Why do I expect trouble if I take cesium and mix it with fluorine?
The location on the periodic table.
Yeah, the location on the periodic table gives me a clue. And based on the location, fluorine wants what? 1 electron. And cesium can easily lose 1 electron. And so I see something happen there. And what's going to happen is the fluorine's going to attack the cesium and take that electron. Cesium will probably resist a little bit, but it's hard because cesium is what you call a big atom or a small atom. It's big. Big. And that electron can be kind of far out from the nucleus. The nucleus is holding the electron in, and the electron's far away from the nucleus. It's easy to steal. So fluorine can come along and pluck that electron off cesium easily. And what we could have is a violent reaction. So what we say is this. We say fluorine is electron poor. It wants electrons. Cesium's electron rich. So it just makes sense. Electron rich, electron poor. Something's going to happen. That'll be very violent.
Is it the same or similar principle in battery electrodes?
Yeah.
This kind of a matter?
Right. It's the same kind of principle with batteries. Batteries operate like that. One side's electron rich, the other side's electron poor. Electron poor side's going to pull the electrons away. In batteries, they have to pull it through a wire. They pull it through a wire. So
what is the electrolyte in the battery?
electrolyte is to prevent too much voltage from building up. Too much voltage. Voltage is like the separation of charge. And so electrolyte is just to maintain electrical neutrality. Electrolyte can be anything. Its job is just to neutralize negative charges and neutralize positive charges. So the voltage doesn't build up. It's called a space charge. Space charge doesn't build up too high. Because if you keep taking electrons, it becomes unstable. So fluoride, if you have a whole bunch of fluoride, you think, okay, fluoride's great. Fluorine wants an electron, you have it. But you can't have a bottle of pure fluoride. That's because it would all be negatively charged. So if you had a bottle of pure fluoride, that would have a super high voltage. It'd have a super high voltage and it would discharge like a lightning bolt. This is too much, too many electrons concentrated. And so we need is something to balance out that charge. What balances out that charge? Yeah, so we could have cesium fluoride. So if we have cesium ions and fluoride ions, then it's fine. Like this. I can't have lattice just of pure nitrate. The voltage would be too extreme. I have to have ammonia in there to balance out the charge. And so we get something stable like that. And so the cesium would be acting like as the salt, the electrolyte there to help neutralize the charge so that fluoride can hold on to that electron. I see the same thing here. There's some other rules. Like this doesn't look so happy here. Like fluorine and chlorine, are fluorine and chlorine compatible? Compatible meaning non-reactive. Yeah. Fluorine and chlorine, fine. I can mix fluorine gas and chlorine gas. I'm not going to worry about an explosion. Basically. Those are compatible. I can take cesium and rubidium, mix them together. If I take cesium and mix it with water, then yeah.
Ammonium nitrate's pretty reactive, right?
Yeah,
That's what
ammonium
most, like,
nitrate is like that. And so this is why they show this thing here.
Wasn't that explosion in Lebanon caused by?
Yeah, right. Beirut. Beirut was caused by ammonium nitrate. Oklahoma City, ammonium nitrate, plus some other stuff. This was the federal building in Oklahoma City. I think 170 people died. More than 170 people died. So, there's an even more massive explosion, but there are fewer deaths. I think there are only 100 deaths or something. I have a video of it. Now Beirut, there's lots of videos of that as well. That was a huge explosion. I'm gonna take a look at this one. This one happened in China. So, have you heard of this one? This is the sensor group.
Video. What the? I think that might be a gas station or something. Whoa! What the? No! No, Disney! Oh no! Are we dangerous here? It's more dangerous. Oh my God! Oh dear! Are you filming? Yes, I'm filming! Wow! I didn't see a thing. Let's go! Let's go down! Let's go! Come on!
Yeah.
Question?
Because you can't like comprehend it. Seeing it in person, like, you just have
The reason is this. This is why I started. You remember oxidation states and oxidation numbers? In the supplement, there's some rules. There's also some rules in our book, but they don't come until much later. Not until chapter 19, section 19.3, oxidation numbers. Well, this is the set. They have 5, which are slightly different than the ones in our book. We'd use these ones here instead. But oxidation numbers will, when we have a formula like that, then we start to think. So we have the composition. We want to know what the structure is. So ammonium nitrate forms what we call an ionic lattice. So we got the composition and the structure. Can you tell me the properties of ammonium nitrate? What are some of the properties of ammonium nitrate? Well, it is explosive. How did you know that? You knew that by empirical data, empirical evidence. Well, there was an explosion, therefore it's explosive, right? But we want to dig in a little bit deeper than that, because do you want to memorize every explosive combination? Because there are a lot, right? It's probably better just to learn something where, some kind of pattern where you can kind of figure out if it's going to be explosive or not. And so this one's easy to figure out that this is a dangerous combination. And one of the first places we start when we're looking at properties, like for example, hydrogen peroxide, you don't want to drink this stuff, but water, no problem. So dihydrogen monoxide, okay, but dihydrogen dioxide, hydrogen peroxide, no. Why? Well, you can memorize it, or you can try to figure it out, you know. Or, you know, superoxide. I mean, people go and buy supplements, antioxidants, superoxide dismutase. And people spend a lot of money on those. I haven't bought any superoxide dismutase, but I've thought about it. Maybe I should buy some superoxide dismutase. What does it do? It's an antioxidant, and it let's see. Yeah. There are other antioxidants we could take. Vitamin C is an antioxidant. You know, so Linus Pauling, have you heard of that guy? Linus Pauling won the Nobel Prize. He's a professor at Caltech, and he's very, very famous. But one of the things he's most famous for is vitamin C. He was a big promoter of vitamin C. And Linus Pauling advocated consuming grams of vitamin C. He ate grams of vitamin C per day. I think it was 1 gram of vitamin C. And so he's actually quite famous for his work in the theory of chemistry, but he's most known for vitamin C because he's like Mr. Vitamin C. So Pauling suggested in the early 1970s that the optimum daily intake may be about 2,000 milligrams of vitamin C. 2,000 milligrams is how many grams of vitamin C? That's 2 grams of vitamin C a day. I don't take that much. That's a huge amount, isn't it?
Why does that?
I don't keep track of how many milligrams.
Mine was 15.
1,500 milligrams? That's 1.5 grams. So you're almost there. Another 500 milligrams will be there.
I got the ones as a kid, and then I started taking them again.
As a kid, you took 1,500
No,
milligrams?
not 15. That was like the Flintstone ones.
Oh, the
There's
Flintstone.
another brand.
Flintstone doesn't have that much, does it?
No, I'm
Yeah.
talking about the ones that I take.
Yeah. Dr. Pauling, for whom the Linus Pauling Institute based his own recommendations for vitamin C largely on theoretical arguments. So it's based on the theory he advocated this. In developing his recommendations, he used cross-species comparisons, evolutionary arguments, the concept of biochemical individuality, and the amount of vitamin C likely consumed in a raw plant food diet. Using this approach, Dr. Pauling suggested in the early 1970s that the optimum daily intake may be about 2,000 milligrams of vitamin C, and that everyone should get at least 200 to 250 milligrams, so a quarter of a gram a day. But he went on a big push advocating this. And so he's already passed away, but you know, when he was alive, he was on many TV shows talking about this. But vitamin C is an antioxidant. You know, let's see, superoxide dismutase. There are lots of antioxidants that people take for just general health reasons. $299. Anti-superoxide dismutase antibody. Oh, okay. This is for research. Therapeutic potentials of superoxide dismutase. Dismutase is an enzyme.
Yeah,
It's from the NIH, National Institute of Health. Superoxide dismutases constitute a very important antioxidant defense against oxidative stress in the body. Did I show you the hypothesis from Dr. Schwelt, MedCram? You know, he's saying that COVID comes in and causes oxidative stress, which leads to superoxide formation. Superoxide dismutase is an enzyme that gets rid of the superoxide, basically. The enzyme acts as a good therapeutic agent against reactive oxygen species-mediated diseases.
I just like put a name.
The present review describes the therapeutic effects of superoxide dismutase, SOD, in various physiological and pathological conditions such as cancer, inflammatory diseases, cystic fibrosis, ischemia, aging, rheumatoid arthritis, neurodegenerative disease, and diabetes. And so people take it for these types of things. They're worried about oxidative stress. Oxidative stress is you have things in the body. Do you want much peroxide in your body? No. And so people take antioxidants to lower. Do you want much superoxide in your body?
Probably not.
No. And so this is the reason people take these. Now, for Dr. Schwelp, he recommended an antioxidant called N-acetylcysteine. Have you ever heard of that? The reason he recommended N-acetylcysteine is it closely mimics the natural antioxidant found in your cell. The natural antioxidant found in your cell is based on cysteines and amino acid. So N-acetylcysteine is very, very close. So during the COVID crisis, he was recommending that people take NAC. So I bought some bottles. I bought about 5 bottles of NAC, and I was taking NAC during the first loop of COVID. And then, oddly enough, NAC was banned. Lots of people were taking NAC well before COVID, and it's been taken for a long time. And yeah, right. That neutrotherapy stuff. It's basically amino acid, and so it was banned for a while. It was banned for like 6 months or something.
Because too many people are taking it.
I think so. Too many people were taking it, and maybe they got false hopes that it would help them with COVID or something. I don't know. They had another reason it was banned. They said it's been around for decades, so why ban it now? You know?
It wasn't a problem before.
It wasn't a problem before then, but then they said now it's a problem. But now, so I bought it on Amazon, and then I couldn't buy it on Amazon. It was gone. But now it looks like the ban was revoked because it was such a ridiculous ban that I think you can buy it now again. So weird. So anyway, these kind of processes are very important. They're very important in the body. They're very important in chemistry. And to get a better idea or better handle, we need to know oxidation states. Because oxidation states are going to be the first clue into how these types of things behave. So when we look at ammonium ion, the first thing is let's figure out what the oxidation states are. The oxidation states of the apparent charge. We're going to use the rules from the Chem 4 book from chapter 19. And so let's go through ammonium and then figure it out. 1, the oxidation number of each atom, number and state, same thing, in any elemental substance is 0. Okay, this is not an element, this is an ion. And so rule 1 does not apply. Rule 2, the oxidation number of monatomic. This is not a monatomic, this is a polyatomic ion. Rule 2 does not apply. Rule 3, the oxidation number of combined oxygen is -2. There's no oxygen, doesn't apply. 4, the oxidation number of combined hydrogen is +1. Well, here we are. So finally we have oxidation numbers and oxidation states. I like to write like this in parentheses. So hydrogen is +1. Now when we do hydrogen as +1, that's for 1 hydrogen. How many hydrogens do we have? 4. So each hydrogen is And we have 4 of those. And so this is the oxidation state or oxidation number. This plus 4 is called the total positive charge in this. Rule 5, in any molecular or ionic species, the sum of the oxidation numbers of all atoms in the molecule of polyatomic ion is equal to the charge on the species. So how many nitrogens do we have? 1. And what is the charge on this? So we have 1 nitrogen, and that's got to equal the total charge. The total charge is plus 1. And so you're right, it's 3 minus. These I like to write as minus 3. And so the oxidation state on nitrogen must be minus 3, because minus 3 plus 4 gives us plus 1, the overall charge. Okay, so that's fine. Well, that's fine for nitrogen, because nitrogen's charge ranges from what to what? Yeah, minus 3 to plus 5. So, you know,
The plus 1 for the hydrogens. Where is that coming from next to the plus 4?
okay, this plus
Or just
1,
say equals.
this is the total charge, total net charge. So this one doesn't belong to anybody. This is just combining all the atoms. So if this is minus 3 plus 1 plus 1 plus 1 plus 1 gives us plus 1.
Okay.
And so that's what we call the net charge. Yeah. Now for oxidation states, we have to memorize a few things, because a minus 3 on one element might not be the same as a minus 3 on another element. So, for example, a plus 1 on hydrogen is no big deal. How do I know plus 1 on hydrogen is no big deal? Because of water. You know, we did water before. What is oxygen in water? Yeah, oxygen likes to be -2. That means hydrogen must be plus 1 on each of them. So we got plus 1, plus 1. Is water very reactive, or is water quite stable? It's stable. And so what we know is that a plus 1 on hydrogen is fine. It's not very reactive. A minus 2 on oxygen is fine. It's not very reactive. What about a minus 3? Minus 3 on nitrogen should be stable, because it should be happy. Nitrogen wants to have 10 electrons like neon. So if nitrogen, which has 7 electrons, gains 3, that has 10 electrons, right? And so you think it's stable because, but yeah, it's happy. It's very happy. This nitrogen is very happy. You know, it's got, if these were gold coins, nitrogen has 3 gold coins, right? 3 extra gold coins. Actually, how many total gold coins would it have? If the electrons were gold coins, it'd have a total of 10 gold coins. But the situation is this: it's stable as long as it isn't attacked by anything. You know, it can live its nice life. But if somebody comes along and says, that's a lot of gold coins on nitrogen, can nitrogen hold on to those gold coins and beat others off? And so that's the situation. You know, okay, if you have 1 gold coin, maybe it's easier to hold on to. 2 gold coins for oxygen is no problem. It holds on to these tightly. So if somebody tries to come in and steal these from oxygen, it's going to have a hard time. But nitrogen's got 3, so nitrogen is really rich with gold coins. But it has a hard time holding on to them because it has 10 negative charges and 7 positive charges. So it's only got plus 7 in the nucleus.
So the further the element or the atom is away from its neutral states in terms of oxidation, the more unstable it is. So the more likely it is to just break apart.
Yeah, I mean, this is good, but then it depends. There could be somebody who wants those gold coins more. And so nitrogen's very rich with gold coins, but it's also kind of big and it's got a lot of them. And it doesn't hold on to them so tightly. Oxygen holds on to them tightly. How about fluorine? Fluorine only gets 1, and it holds on to it so tightly that it's really hard to let go. And so fluorine holds on. But nitrogen, you know, so something like oxygen with a -2, we wouldn't call electron rich. It's just happy as is. Fluorine with a -1, it's happy as is. But nitrogen is kind of rich for the taking, because if something came along, it could take that or take some of the electrons away. You know, what else is rich? We've seen this before, like methane. Methane's quite rich. So we follow the rules. 1, 2, 3 don't apply, 4 doesn't apply. So in methane, what is hydrogen? Plus 1. And that means carbon is minus 4. So the way you figure that out is plus 1 times 4 gives us plus 4. Plus 4 plus what gives us 0. There's no net charge here. And so it's got to be plus 4 minus 4 gives us 0. And we only have 1 carbon, so that carbon's got to be minus 4. Is that carbon rich? That carbon's got 4 extra gold coins. It's very rich. Well, somebody can come along and take those. Oxygen. Oxygen wants how many? 2. So oxygen comes along and sees carbon has this excess of gold coins. And so there's going to be a reaction here. And in fact, oxygen not only takes the 4 extra gold coins that it has, but it's going to take even more. It's going to take everything it can take from carbon. What is everything it can take? Well, it's going to go to CO2 and, well, we'll just stop there. Now, let's see what happened to carbon. Carbon used to have 4 extra gold coins. Now what is it? Well, when we look at this, oxygen is minus 2. We have 2 of those. So minus 2 times 2 is minus 4 plus what gives us 0? Plus 4. So carbon used to have 4 extra gold coins. It lost those 4. Not only did it lose those 4, but it lost an additional 4. So it lost a total of 8. So each carbon lost 8 electrons to oxygen. Well, oxygen is going to be very happy. And we end up with this. In water, it's minus 2, so those oxygens, and then in hydrogen, it's plus 1. Plus 1 for hydrogen is no problem. And so this is what we say. In terms of relative, plus 1 on hydrogen is no big deal. This is what we call electron rich. Why is it electron rich? It's electron rich because carbon is in the minus 4 oxidation state. That's rich. We go to oxygen. What's the oxidation state on oxygen? Here, rule 1 applies. Rule 1 says that the oxidation number of each atom in an elemental substance is 0. So what we're going to have is 2 times 0 is 0. We call this electron poor. Well, it doesn't look so poor, but this is electron poor. It wants it. Oxygen is a good oxidizer. It wants electrons, right? And so we have electron rich and electron poor here. But when we go to carbon, you think, wow, now carbon is plus 4. Carbon's plus 4, isn't that really electron poor? And here you need to have some empirical data memorized. And the empirical data is from observation. Is CO2 a very reactive chemical? No, it's not. It's very stable, right? And so this is okay. You know, this is neither rich nor poor. It's okay. How about water? Is water rich? Is water poor? Water's okay. So electron-rich species are called the fuel. And electron-poor species are called the oxidizer. And when you have a fuel and an oxidizer, you're either going to get a fire, or you're going to get oxidation, or you're going to get an explosion, right? You can have an explosion with gasoline. You can have an explosion with methane. And so this is a bad combination. It's a bad combination because you're taking an electron-rich species and you're mixing it with an electron-poor species. Now, this is electron-poor, right? Or it seems to be, but here we have electron-poor species. Is this electron-rich? Are we going to get an explosion by CO2 and water? No, we get like carbonated water. Perrier or something. That's it. Or yeah, sparkling water. And so it's not a problem. And so this is as is okay, as is okay. So we need to know what the numbers mean, like this. And so in this case, this is a fuel. Ammonium is a fuel because when I look at ammonium, nitrogen is -3. A -3 on nitrogen is kind of rich. That's what I see. How about nitrate? I mean, how can it be rich? Because ammonium has a positive charge. This perplexes lots of students. A lot of students are perplexed because ammonium's positively charged. How can that be electron rich? Electrons are negatively charged. But we don't think in terms of the overall charge because the hydrogens are fine with +1. The +1 comes from hydrogen. The richness comes from nitrogen. How about nitrate? So let's follow the rules for nitrate. The rule 3 applies. Oxygen is -2. So nitrate's got to be rich. Nitrate's got to be rich because it has a negative charge, right? Negative charge means it's got to be rich. Right? No, that's wrong. Oxygen would be -2. How many oxygens do we have? 3. So 3 oxygens, each at -2, gives us a total negative charge of what? 6. So -6 plus what? We only have 1 nitrogen. -6 plus what gives us -1? Plus 5. So I'm not going to write Roman numerals here because these are oxidation states, not charges. So we'll write +5. This is the parent charge. What would you say about nitrogen here? Would you say it's rich because nitrate has a negative charge?
Nitrogen.
Nitrogen. No. Nitrogen is
Electron-poor.
electron poor. And so here we have an electron-rich nitrogen. Here we have electron-poor nitrogen. Is that an equitable situation? One nitrogen has lots of gold, the other nitrogen has nothing. What do you think is going to happen when you mix these together? Reaction. Yeah, so this is unstable. This is electron poor and electron rich, but the problem is they're in the same compound. So as long as they stay in their positions, respective positions, then nothing should happen.
Maybe disturb it or add a catalyst, it can set up the reaction, right?
Right.
So, because you actually have an oxidizer in it.
Yeah. Electron poor species, so this is the fuel. Electron rich species is the fuel. And electron poor species is the oxidizer. So we call this metastable mixture. Metastable mixture means it's not really stable. It's like gasoline and air, you know. You always got to worry in the back of your mind, you know, if it catches on fire, you're in trouble. Or methane. If I fill up this room with methane in air, it's metastable. Hopefully it doesn't explode. Chances are it won't explode, but it might explode. And so that's metastable. This is the same thing. Hopefully it doesn't explode. Hopefully,
So, is the stability in the structure of the mixture?
Yeah, the stability in the structure. Right now, they're separate. But what happens if you get this hot?
They vibrate.
It vibrates. And the hotter and hotter you get it, the more it vibrates because you're going to get more and more kinetic energy. And eventually, what's going to happen is there's going to be so much kinetic energy, it's going to go, you know, the two are going to collide. And then what's going to happen? Yeah, you're going to get a reaction. So one thing is, a lot of these you keep in the refrigerator.
That's a transverse metric rate.
Well, how it vibrates?
Because, no, the reaction, because it will happen in all directions.
Yeah, it should happen in all directions. This is when you're three-dimensional. And so you should have, well, there are different types. There's like different types of explosions. There's detonations, there's deflagrations, which are like high-speed combustion, different types of explosions that you can get into. But one thing to stabilize this, maybe we'll throw it in the freezer or in a refrigerator. That'll help stabilize it because that'll cool things down. We definitely don't want to heat things up because heating things up could cause problems. And we don't want mechanical stress. Do you want to be jumping up and down on this? You don't want to be jumping up and down because you could be forcing the ions closer together. And once they get close enough, then we're going to have a reaction. Because if the nitrogen's in the tug of war with another nitrogen, who's going to win? It's nitrogen versus nitrogen.
So it's also because nitrogen and oxygen on the reactor are close to one another, they don't hold on to each other that well. So it's easy to just pull them apart and have reactions.
Well, actually, they hold on to each other pretty well because what it turns out there's another way that we can get to 10 electrons, and the other way we can get to 10 electrons is not taking. This is taking them. The other way we can get to 10 electrons is by sharing them. And so the nitrogen and oxygens hold on to each other pretty well here. The nitrate itself is not inherently unstable. So for example, if this were sodium nitrate, no problem. I would never worry about sodium nitrate. Sodium nitrate, no big deal. Why?
It's a salt.
Well, this is a salt too. Ammonium nitrate's a salt. Any ionic compound is called a salt.
Is it because of the position of the reactor?
Not based on the position of the periodic table. It's based on this. Nitrate's still an oxidizer. Nitrate is still electron poor. But sodium is, what's the charge on sodium? It's +1. Is sodium a good fuel? Is sodium electron rich? Can sodium lose any more electrons? There are no more electrons for sodium to lose. Because once it goes to +1, then it's happy with a neon, and then it's going to stop there. So here we only have the oxidizer. And so this is it. If I fill up this room with methane alone, then there's no big deal because it's only methane. Or if I only have oxygen in this room, it's not a big deal. I need fuel and oxidizer together. And so this one is only fuel. No fuel, just only oxidizers. We have the oxidizer, but this is not a fuel. And so sodium nitrate is stable. I could jump up and down on it. I could heat it up. I'm not going to worry about it. Sodium nitrate at all. But ammonium nitrate, I'd worry about.
How do they make ammonium nitrate without causing an explosion?
Oh, you talked about that the first day of class.
There are lots of ways to make it without an explosion.
Isn't water a reactant for ammonia? Is that a different compound?
That's a different one. Water, well, I'll get back to how to make ammonium nitrate. I'll tell you how to make ammonium nitrate, but you still got to worry. We have ammonium nitrate. It's just when you concentrate it. So if you dissolve it in water, it kind of dilutes it down, and then you can concentrate, evaporate all the water. When you evaporate all the water to collect ammonium nitrate, then you could have trouble, potentially. But as long as it doesn't get too hot, you're okay. So you don't really have to worry about it exploding. Water is normally very unreactive. But water can you burn water? Yeah, you can burn water as long as you have something powerful enough to take electrons from oxygen. And so you might be able to burn water, let's say in fluorine. You might be able to get it to burn. The other thing is hydrogen electron poor? No, not really. Hydrogen is happy as is, but if there's something that's even richer, something very rich, like cesium, if we have cesium atoms, cesium, even though there's no charge on cesium, cesium is very rich. It has lots of gold coins for the taking, or only one. One gold coin for the taking. And so that means water can come in and take it. If water comes in and takes that gold coin from cesium, then hydrogen gets it. And if hydrogen gets it, then we form H. But H doesn't like to be alone, so there's got to be another H, and we form H2. And so this is what happens. When cesium reacts with water, water acts as the oxidizer here. Cesium is the reducer, the fuel, and it's a great fuel. Cesium can easily burn, and we form hydrogen. Or we could try to burn this. We could try to burn this with something like a very powerful oxidizer. So if we have a powerful oxidizer, it's going to take electrons from oxygen. If it manages to take the electrons from oxygen, we'll just form O. But O doesn't like to be alone, so we get O2 instead. So water can either act as a fuel or an oxidizer. It can go either way. Depends on what you react it with, but it's not very reactive. It's quite stable. And so we got to be careful. When you're making ammonium nitrate, you got to be careful. Otherwise, you might have something like that. That was just stored ammonium nitrate. I think only. Have you heard of Texas City? 600 people died in Texas City. That was ammonium nitrate explosion. So there are lots of compounds like this in chemistry, where you have the fuel and the oxidizer in the same, in this case, in the same lattice. In other cases, you have it in the same molecule. I can just show you one more example here. TNT. No, I better not call it TNT. You know what TNT stands for? Yeah. Trinitro-toluene. This is TNT here. It's a molecule. It's a liquid. TNT. This is the structure of the molecule. Yeah. This is a very interesting molecule. They're very dangerous. Why is this a dangerous molecule? Because these are called nitro groups. And these nitro groups have nitrogen in a high positive oxidation state. We can calculate it, but that's more Chem 1A type calculation. I'm not going to get into it in Chem 4. Chem 1A will calculate all the oxidation states of each of these atoms. And it turns out that these are electron poor. So these three things here, the three nitro groups are electron poor. But the toluene group, which is this is trinitrotoluene. The toluene group is electron rich. They're in the same molecule. So you got these three. This is very dangerous. They're very dangerous. And so you got to worry about this just exploding. And so, Nobel. What is it? Alfred Nobel? He became extremely rich by figuring out how to stabilize this without, it was like you have this stuff and you don't know, is it going to explode? In the next second, it could explode. You don't know when it's going to explode because it's so sensitive. And so a little shock to it explodes. A little temperature fluctuation, it explodes. It's like that. But he won. He won his fortune by stabilizing it. So he stabilized it so it wouldn't explode at the slightest instigation.
But how did he do it again?
How did he stabilize it?
Yeah, it was like it didn't involve mercury or something?
That's a good question. I don't know how he stabilized it. I'm sorry, it was nitroglycerin. Was it nitroglycerin? I don't remember. Yeah, sorry, nitroglycerin. Nitroglycerin is an explosive liquid which was first made in 1846 by treating glycerol with nitric and sulfuric acid. Alfred Nobel worked hard to improve nitroglycerin as an explosive that could be used in blasting rock and mining. He made one of his most important discoveries when he found that by mixing nitroglycerin, an oily fluid, with Kissel or whatever that is, I don't know how to pronounce that. Sounds German. The mixture could be turned into a paste. This material could be kneaded and shaped into rods suitable for insertion into drilling holes. He called this paste dynamite and went on to develop a blasting cap which could be used to detonate dynamite under controlled conditions. So he converted it into a paste using this stuff. What the heck is this stuff? Diatomaceous earth. You know what diatomaceous earth are?
Isn't it just concrete?
No, it's little shells of marine organisms here. But these are not normal shells. You have carbonate, like most organisms have like a carbonate skeleton or carbonate shell. They call it aragonite. Have you heard of it? It says calcium carbonate. In fact, at UCSB, they were studying aragonite in the form of abalone shells. Have you ever tried to break an abalone shell? Extremely difficult to break. And this is made out of calcium carbonate plus some other like biopolymer type stuff. And so what they're trying to do is they're trying to develop a tough material like abalone shells, but something that humans can make rather than abalones. Because abalone shells have really good, this is in the material science department at UCSB. And the material science department at UCSB, they were looking at abalone shells, spider webs. Spider webs are stronger than steel. So if you can make a spider web that's thick, you can make things out of spider web instead of steel. It'd be a lot lighter. And it has a tensile strength stronger than steel. But diatomaceous earth, these little shells are made out of silicate rather than carbonates. And so you can spray acid on these and they don't dissolve. They use diatomaceous earth for different things. And in Santa Barbara, there's a diatomaceous earth mine there, where there are larger deposits of diatomaceous earth in Santa Barbara County that they use to dig out. I guess create a home would be cool. So that's pretty interesting. Just mix this with nitroglycerin and make a paste. This would be an inert ingredient. It really doesn't do anything. And so it just stabilizes it by making a paste rather than a liquid. A paste is a semi-solid. Semi-solids react slower than liquids. It's like thermite. I wouldn't, those guys that were working with thermite, no goggles. Were they wearing gloves? Do you remember? Do you remember the videos? The Brainiacs? They didn't even have safety glasses. They didn't have one of those bomb crew suits, those space person looking suits. They didn't even have that. Why? Because they didn't have to worry. They didn't have to worry. I wouldn't worry about thermite reacting like that.
Isn't it so hard to get it to react?
It's so hard to get it to react because thermite consists of solids. So you have aluminum crystal and a rust crystal, and you got to get them to react together. Are they going to react together? So solid-solid reactions are. And so here's my aluminum chunk, Here's my rust chunk. What's rust called? The name of this, Fe2O3 is rust. Iron oxide, but we have two iron oxides. We have this iron oxide and there's another iron oxide. Yeah, the other iron oxide is FeO. So we have two of them. So this one is called, let me tell you what this one's called. This one's called iron, Roman numeral 2, oxide. So what are the two common charges of iron? 2 and 3. And so this one's called iron 3 oxide. We can easily figure that out because each oxygen is -2. If each oxygen is -2, we have 3 of them. That gives us -6. That means the irons have to be +6. We have 2 of them. That means each iron must be +3. +3 + 3 gives us +6. And so this is called iron 3 oxide. But you could jump on this, and it's not really going to do much to get these to react. What we need to do is we need to get the electron-poor species to react with electron-rich species. Which species is electron-poor? The iron 3. Iron 3 is the electron-poor species. Which is electron-rich? The aluminum. But, you know, iron 3, is it going to be anything comparable to, let's say, nitrate? No, probably not. So I don't expect much of a reaction. This is rust and aluminum. But what they did was they put, remember they lit the touch paper, they called it, the touch paper? And the touch paper, what it did was it got this hot. And it got it hot enough to melt the aluminum. When the aluminum liquefies, then you got to watch out because liquids can react fast. And so liquids will have no problem attacking, or iron attacking the liquid aluminum. And so they just got it to melt the aluminum, and then once the aluminum melted, then the reaction started, and then it won't stop, basically. And so solid-solid reactions are slow. And so this is why it makes sense. Nitroglycerin, if you could get it semi-solid, then it's going to slow things down. You don't have that translational mobility that you once had. All right, let's see. Let's take a break now. Then we'll start up again. Do the break. Do you know what bleach is made out of? Bleach. It's alkaline, yeah. That's correct. That's a property of bleach, but what is it made out of? If you look on a container of bleach, you'll see this ingredient: sodium hypochlorite. Sodium hypochlorite. What's the formula for that? Well, I know the sodium hypochlorite. I know sodium ions. Sodium ions are Na plus. What is hypochlorite? ClO charge minus. And so you either have it memorized or you can just get it off. I would get it off periodic table. I know what chloride is. ClO3, chloride would be ClO2, hypochlorite would be ClO. And so we have sodium hypochlorite that's in water is called bleach. And there's a rule, safety rule. Have you ever heard of the safety rule? Never mix ammonia with bleach. Yeah, it can make some dangerous gases, and you could have potential explosions. And so we never mix ammonia with bleach. This is a bad combination. It's a bad combination because of what? How can I tell I'm going to get a reaction here? Well, one of the first things I do is I'd look at the oxidation states. Sodium ions are pretty stable. People eat those. sodium ions. But hypochlorite, I wouldn't necessarily eat that. If you had sodium chloride, yeah, sodium chloride you could sprinkle on French fries. But sodium chloride, hypochlorite, bleach crystals, I wouldn't sprinkle on French fries. Well, it wouldn't taste very good. You know, I know the taste of bleach. Did I tell you about that? I didn't tell you about it. I know the taste of bleach. I know the taste of bleach because when I was in the Boy Scouts, we had bleach tablets. Yeah, which are just bleach tablets, sodium hypochlorite tablets. We had that, which is a solid, and you mix it with water, and then you get bleach. It's also called chlorine water because when you mix chlorine with water, it forms sodium hypochlorite or forms hypochlorite ions. And so we used to carry these sodium hypochlorite tablets for water purification. And so I remember being in the mountains behind Ventura. In the summer, it's very dry. There's not much water. And so you get these creeks that are mostly dry, and then you'll hit a little pocket of water. But the pocket of water is so stagnant. You know, there's no water flow. There's nasty stuff growing in it. It kind of looks like a cesspool. And so I filled my water bottle there and put some bleach tablets in there and then shook it out and then drank it. I was drinking bleach. I don't recommend drinking bleach. It's not very good. I know it was recommended for killing COVID, but it could end up killing you as well. But you don't want to mix sodium hypochlorite with ammonia. Those are two common household cleaners. People use bleach to clean, people use ammonia to clean, and this is a common mistake. And we know that there's going to be a reaction there because when I look at sodium hypochlorite, I see what? What do you see as far as reactivity goes? You know, for example, sodium chloride is generally regarded as safe. Of course, you don't want to eat too much salt. Too much salt can also kill you. You know, there is a lethal dose of sodium chloride. But that lethal dose is so high that nobody's going to hit that. Sodium chloride is stable, safe, people eat it. Sodium hypochlorite is not so stable. It's great at killing. It's great at killing viruses and bacteria. You know, you're worried about E. coli or something like that. Actually, sodium hypochlorite bleach is a wonder chemical. I used to use bleach a lot. You know, not for killing bacteria and viruses. I used to use it for killing odors. I used to work with H2S, you know, hydrogen sulfide. And hydrogen sulfide smells like rotten eggs. And so what I do is I just bleach the heck out of it. Because what that does is it converts this rotten egg type thing, and there are a whole bunch of rotten egg style compounds. We use skunks, have lots of them. And then hit it with bleach. Bleach it out, it converts that into things like sulfate. Sulfate doesn't have any smell to it. It's fine. So I used to use a lot of bleach. One time, one of the guys working at the lab at UCLA spilled a little bit of rotten egg smelling liquid on his brand new tennis shoes. Yeah. He tried to bleach it out, but it didn't work. And so he ended up, they smelled so bad, he ended up having to throw them away, and they were very expensive tennis shoes at the time. But that's what you get for wearing expensive tennis shoes in lab. You want to wear junk clothes in lab. You know, clothes you don't care about, or wear a lab coat. I have another friend who's a biochemist. He went to go work for the Army. He has a PhD in biochemistry. He went to go work for the Army in Maryland. And do you know what he works on? nerve gas. You have nerve gas? Nerve agents? They have some liquid nerve agents. He was telling me, like they're looking at if you spray like nerve agents on plants, like leaves of plants, and you walk by the plant and a little droplet of nerve agent gets on you, it's lethal. You could die. So was he making nerve agents? No, he wasn't making nerve agents. He was looking at ways to disarm nerve agents. Do you know what he said? I asked him, what do you use to, not water. You know what he used to kill off the nerve agent? Bleach. Just bleach the heck out of it. Bleach the leaves. So, you can imagine people walking around bleaching. Or, they had that, they had in Tokyo, they had the nerve, somebody did released a whole bunch of nerve agent in the subway in Tokyo. And people should come there and just bleach the heck out of everything, kill it off. Because if there's nerve agent all over, let's say the subway station, you touch something, then you got to worry, because it doesn't take much to kill you. Well, that's, bleach is a wonder chemical. I use a lot of it. Still use it. It's great at getting rid of mold. But anyway, tell me why you think bleach is reactive. Well, so what's the first thing we do? The first thing we do is look at. Well, we know the composition of bleach. The composition of bleach: 1 sodium, 1 chlorine, 1 oxygen.
Look at the oxidation state.
Yeah, we look at the oxidation states. So what are the oxidation states there? So sodium is easy, that's +1. Now chlorine versus oxygen, we can follow the rules. My set of rules is easier. The species on the right always wins. And so both of these want electrons. Like chlorine wants 1 electron, oxygen wants 2 electrons. So who wins? Chlorine versus oxygen. Oxygen wins. And if oxygen wins, how many electrons does it get? 2. So oxygen's -2, and therefore chlorine must be what? It's got to be +1. Yeah, +1. Now chlorine, we have to know this. Do you want to breathe this stuff? No. If chlorine gas, what's the oxidation state of chlorine gas? This is rule 1. It's not -1, because if this were -1, -1 times 2 is -2. It doesn't add up. It has to be 0. And so even though this is 0, we call it electron poor, because what it wants is it wants 1 more electron to be chloride. Once it's chloride, it's happy and it's stable. We can eat this stuff, but we don't want to eat this stuff. Well, would you want to eat this stuff? No, because this seems even worse, because chlorine is not 0, it's actually +1, which makes it more reactive, which means that sodium hypochlorite must be a great oxidizer. Yeah, and so this is a good oxidizer. And so what we say is, even though this is only +1, hydrogen is +1, but this is different. This is chlorine. Chlorine in the +1 is not good. And so that makes this an oxidizer. And so this is electron poor. But what about ammonia? So we follow the rules. We go through hydrogen. Hydrogen goes +1, and then that means nitrogen is -3. And we call that electron rich. You would say it's neutral because nitrogen wants those 3, but it's hard to hold on to that many. And so this is electron rich. Whereas oxygen here, it's -2. You might think that's electron rich, but that's happy as is. This is electron poor. What's electron poor? The chlorine is electron poor here. The nitrogen is electron rich here. And so what we're going to have is we're going to have a reaction. And then in this reaction, what are we going to form? Well, if chlorine takes an electron, it can form chlorine gas. Or chlorine takes an electron, it can form chloride. Or we might have a combination. So for example, we might have chlorine monoxide, chlorine dioxide. Do you want to be breathing in chlorine monoxide, chlorine dioxide gas? No. Those are dangerous gases. And so not only can this cause an explosion in your sink, and there's lots of cases where it has exploded in the sink and generates gas, and it causes an explosion, and if your face is above the drain, it gets into your eyes, whatnot, and you don't want a whole bunch of bleach getting into your eyes. Can cause an explosion, but it can also generate dangerous gases, chlorine oxide type gases. Okay, so that's so a lot of these safety rules, we could memorize them, but there's too many to memorize. There's no way you're going to memorize every incompatible combination. So what we have to do is we have to look for patterns, but we don't have to sit there and memorize every single one.
Now, I have a question. So, acid is with hydrogen, right?
Yes.
And this is with oxide, this is oxide. What reaction makes the acid burn and then oxidize? What is the difference between the acid and the oxide in the reaction?
In a reaction, those are two different types of reactions usually. When we have an acid, it usually involves in an acid-base reaction. There's usually no change in the oxidation state. And so if we take an acid, like let's see, what would be an acid? Vinegar. Vinegar is acetic acid. And let's say you don't like the smell of acetic acid. Vinegar has that smell. You know that smell?
Yeah.
Kind of a rancid smell. You can neutralize that smell easily. You know how you can neutralize that smell? With a base. A base will neutralize it. And so we can neutralize it with any base that we want. What's a good base? Like Tums. You know what Tums has in it? Tums, I think, is calcium carbonate.
Yeah, calcium carbonate.
Yeah. So we can put in some Tums in there, calcium carbonate. And what that's going to make is it's going to make calcium acetate. Calcium acetate is like this.
Is it still acid?
No. So this would be calcium acetate, and it's going to make what's carbonic acid. Carbonic acid is an acid. This is carbonic acid, but carbonic acid is unstable. Carbonic acid decomposes into water and CO2. So when you take an acid and mix it with Tums, it could start to bubble like this. And that's neutralizing the acid. So we no longer really have the acid. CO2 is actually an acid as well, but it doesn't begin with an H. When we look at the oxidation states, none of the oxidation states change in this. This is acid-base reaction. Whereas this is what we call a redox reaction. The oxidation states do change here. So for example, in H2S, it's +1, and sulfur is -2. Well, -2 on sulfur is much different than -2 on oxygen. -2 on oxygen is stable. A -2 on sulfur is rich. Sulfur versus oxygen, which one's bigger? Sulfur or oxygen? Sulfur is a lot bigger. And so if you have a -2 on sulfur, it's a big atom. And so it's a big atom with 2 gold coins extra. And so it's easy to take those. Whereas oxygen, which is a small atom, it's hard to take those. And so sulfur, it's easy to take. We use some bleach. Bleach is powerful enough to take those, and we form this, sulfate, which is bleached out. And so this is how I got rid of most of the smells. Everything smelled. And so at the end of the day, I just start bleaching everything out because it smelled bad. All right, so that's the beginnings of some properties. And when we're dealing with composition, we want to understand some properties. And start doing that. And one of the properties is electron poor, electron rich. These properties are called redox. Stands for, oxidation reduction. Redox type interactions. We're going to look, yesterday we were trying to predict some of those, but we couldn't predict some of those because some of those are not redox reactions. In addition to redox reactions, we have acid-base reactions we have to worry about, which we were talking about. In addition to acid-base reactions, we have metathesis reactions. So, probably the easiest way to make ammonium nitrate is via metathesis reactions. You just find ammonium, something that contains ammonium, you find something that contains nitrate, and bring them together. And then you can have ammonium nitrate. That's the easiest. But we're going to leave reactions right now. Reactions start in chapter 8. Chemical reactions. And so in chapter 8, we're going to be looking at this more, but I figured the sooner we start talking about this, the more time you have to memorize how to do these oxidation numbers and that kind of stuff. So I'm trying not to cram everything in right before the test. That's why I'm jumping ahead. So we're going to look at the mole next. So if I have a sample of bleach, I have a sample of CO2, I have a sample of water, I have two choices. I can work with individual molecules or individual formula units. So if I'm looking at a bleach tablet, sodium hypochlorite, I can look at, that's an ionic compound, therefore it forms an ionic lattice. I can look at a formula unit of that. When you look at individual formula units or individual atoms, you want to know, or individual molecules, you want to know what isotopes are in there. So if I go into a sample of water and I pluck out a single water molecule, then I'm going to need to know which one is this. Is this hydrogen 1, hydrogen 2? Is this oxygen 16, oxygen 17, or oxygen 18? But how often do we work with individual water molecules? No, not often. In fact, we work with trillions upon trillions of water molecules. If we're dealing with trillions upon trillions of water molecules, we probably don't want to know, if you have a trillion water molecules, you probably don't want to know which individual water molecules you're dealing with one by one. Let's say, if you're looking at the population of the US and you want to determine like body mass, how much people weigh, do you want to go out and weigh every single person in the US? No, you probably just take the average, right? The average. Well, this is the same thing here. A mole is just a counting unit. And so it's like a dozen. So if I have one H2O, this would be just one molecule. And if I'm working with one molecule, then I need to know, what are the isotopes? I don't want the average. I want to know what it is. If I'm working with a dozen, one dozen would be 12 H2O molecules. Then, maybe I'll do the average. Or maybe I'll look, if I only have 12, I might look, Because the average might be skewed if you only take 12. It depends on which 12 you pick out. And so the average might not be, true, as calculated earlier. And so I might look at it individually. But if I had 6.022 times 10 to the 23rd H2O molecules, you know what I call that? I call that 1 mole of water molecules, 1 mole. And so normally when I'm thinking about water, I can have 1 water molecule, I can have a dozen water molecules, or I can have a mole of water molecules. That's typically what I'm thinking. Yeah. If I have mole water molecules, let's write that in regular, not scientific notation. So I'm going to move the decimal 23 places. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 21, 22, 23. This is only the 4 sig figs. There are actually more sig figs than this. But most people memorize it the 4 sig fig. And so this would be 1,000, million, billion, trillion. 1,000, million, billion. Is that right? 1, 2, 3, 4, 5, 6, 7. No, I miscounted this. So this should be 23, 3, 6, 9, 12, 15, 18, 21, 22. I'm missing one, sorry. Didn't quite look right. That should be it. So this is 3, 6, 9, 12, 15, 18, 21, 22, 23. Now it's right. So what would this be? This would be 1,000, million, million, billion, trillion, 1,000, million, billion. So this would be 602 billion trillion. Water molecules. This is equal to 1 mole of water. Water molecules.
Is there a specific reason why that amount is that? What is that 1 liter?
Yeah, what's the reason why it's such a weird number? It's like 12. Why is 12 a dozen? Is there a specific reason that 12 is a dozen? I was thinking maybe, maybe the best baker in the town had 12 fingers.
But then there's a baker's dozen.
What's that?
But then there's a baker's dozen, which is.
Baker's dozen is 13.
Baker's, well, maybe the partner or somebody else had 13. I don't know. Baker's dozen. Baker's dozen is in case you eat one. That way you have 12 left over. Is that
No.
the reason? That's a tax. I don't know. My baker's dozen would probably have to be 15. Then I can eat 3 and still have 12. Something like that.
I think it's a marketing thing.
Well, there's a reason. There's a reason it's 12, and actually I don't know what the reason is. There's a reason this is 6.022. That's actually more digits, but I don't have those memorized. Times 10 to the 23rd, but I don't know. You know? Actually, I do know. You have to know why this is this weird number. It's a weird number because this is a hard number to remember. Like 12 is kind of hard. Why didn't they pick 10? 10 would be a lot easier. And multiples of 10, 10, 20, 30, 40.
Well, for this joke's sake, I think a lot of like recipes deals in 2s and 3s, so maybe that's why.
Okay.
For like eggs specifically.
Oh, then that makes sense.
Okay.
Because if you go buy 10 eggs, then you can't really divide by 3, so you can't make it. So economic decision. Well, there's a great reason this is this. This is a hard number to remember, but it saves you a lot. And so why such an odd number? Do you know what they call this number? This number is called Avogadro's number. Or Avogadro's constant. And it's just the number. 602 billion trillions, Avogadro's number. Actually, we needed to 4 sig figs, so it should be 602.2 billion trillion. And the reason for this is, where does that number come from? What's the origin of the number? And so the number comes from this. And so let's take a look at the definition of the mole. And so you need to know the definition of the mole. The mole, 1 mole is equal to, or defined, I'll just say defined. 1 mole is defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. So if you had exactly 12 grams of carbon-12 and you counted the number of atoms in there, actually you can't count the number of atoms. You'd have to figure it out some other way.
When it's carbon-12, why is the script like in the top left of the carbon?
The 12 is the mass number, A, so it's usually written at the top left. The other way it's written is like this, carbon-12. So those are the 2 ways it's normally written. Sometimes it's written on the right side, but convention dictates it should be written on the left side. So this is Avogadro's. This is a portrait of Avogadro. This is some other scientists here, Perrin. Perrin made the first accurate measurement of Avogadro's constant, finding that a mole of hydrogen consists of 7 times 10 to the 23rd molecules. The modern measured value is 6.0 times 10 to the 23rd molecules. It's close. So this is, so they calculated it. And so that's what you do, you calculate it. You don't actually measure. So we can calculate how many carbon-12 should be in exactly 12 grams of carbon-12. And that number comes out to this. But still, that's how it's defined. Why was the definition chosen like this? And the definition was chosen like this to make your life a lot easier. So why is this an odd number? It's such an odd number because we have a numerical relationship between formula / molecular mass. Not everything forms a molecule, but everything will have a formula. And something called molar mass. And so it's going to make your life a lot easier. And so an example of this is 1 carbon-12 atom. Do you know 1 carbon-12 atom, how much it weighs? By definition, it weighs
12.
exactly 12 U. So what we can say is there's 12 U's of carbon-12 in 1 carbon-12 atom. But what we can also say is this. Because of the definition, $602.2 billion trillion carbon-12 atoms weighs how much? Weighs exactly 12 grams. And so what we can say is this, there's 12 grams of carbon-12 in 1 mole of carbon-12 atoms. Or if we're looking at average carbon atoms, 1 mole of average carbon atoms weighs 12.01 grams of carbon. And so what it does is, 12 grams is fine. 12 grams is something that we can see macroscopically. And so the same thing. One water molecule weighs 18.02 U, on average. 1 mole of water molecules weighs 18.02 grams. Well, 18.02 grams of water is 18.02 milliliters. So this is 1 mole of water. And this would have 602 billion trillion water molecules. We have 2 moles of water, which would be 36 milliliters. 3 moles of water would be triple that. Half a mole would be like 9 milliliters of water. And so we get this thing. Off the periodic table, the average atomic mass of iron is 55.85 U. But if we had a mole of iron, that would weigh 55.85 grams. And so this would be the molar mass. So we weigh out 55.85 grams, that's 602 billion trillion iron atoms. Off the periodic table, the average aluminum atom weighs 26.98 U. And then if we weigh out 26.98 grams, that would be 602 billion trillion aluminum atoms. Mercury, sodium, copper. There's copper 2 sulfate pentahydrate, mercury 2 oxide, oxalic acid. This is a weird formula for oxalic acid. It's COOH double. Oxalic acid dihydrate is the other one. And so the reason why the mole was defined this way is so that we have this relationship, the numerical relationship. And so when we're dealing with masses, we have a choice of 2 units. And so here, if I look at H2O, the 2 units would be H2O, the average one weighs 18.02. And so we can have the units of U per molecule, or 18.02 grams per mole of molecules. A mole of molecules is something we can easily visualize. We can easily see that. That would be and so typically we work with mole quantities of things. And so let's take a look at the example here, doing a calculation. Let's say I had 9 billion water molecules. Do you think I'd be able to visually see 9 billion water molecules?
Like individually?
No, I mean just as a droplet. Is that a drop or several drops of water? How much water is that?
Yeah, it's like
Maybe not, because that thing there, that's 1 mole, is a billion trillion.
Yeah.
Probably not.
Okay, so let's go. What we're going to do is we're going to calculate the mass of this and the volume of this. And so let's go ahead and do that. If I have 9 billion, billion would be 10 to the 9th. Millions 10 to the 6th, so billions 10 to the 9th, H2O molecules. And then I know 1 mole of H2O molecule contains 6.022 times 10 to the 23rd H2O molecules. And so H2O molecules cancel, and that leaves us with moles. So how many moles of water is that? So it would be 9 times 10 to the 9th. 9 times 10 to the 9th divided by 6.022 times 10 to the 23rd. And I get 3, 6, 9, 12, 15. It looks like at 1.5 times 10 to the minus 15 moles. But moles is still a little bit abstract.
I got minus 14.
Minus 14? Okay. I just did an eyeball count. Let's find this to explain. Okay, then let's go with grams. The average water molecule, is 18.02. It's U per molecule, or 18.02 grams of H2O per mole of H2O molecules. And so the moles of H2O molecules cancel, and that leaves us with grams. And so I'm going to take this times 18.02. And I get how many? 3, 6, 9, 12, 13. What did you get?
2.7 or
Okay.
2.69.
Times 10 to the minus
13.
13?
Yeah.
Okay. 2.69 times 10 to the minus 13, which is 26.9 times 10 to the minus 12 grams. What's 10 to the minus 12 in metric prefixes? Did I go the right way? No, I think I made a mistake. This would be 26.9 times 10 minus 12 or the other way. So if I make the exponent bigger, I got to make the coefficient smaller. So this should have been 0.269 times 10 minus 12. Is that right? Grams. Do you know what 10 minus 12 is? Metric prefix? Have you memorized that yet? It's an important one.
Yeah, micro?
Micro is 10 minus 6. Got it? No. What did you say? Pico?
Yeah.
It's pico. And so this is 0.269 times 10 minus 12 picograms. So how much is that? Well, they say a dollar bill is about 1 gram. So if you take a dollar bill and you cut it up into a million pieces, each piece would be a microgram.
Wouldn't it be 0.269 picograms instead of times 10?
Yeah, 0.269 picograms is right. Thanks. So not even a picogram. So if you take that dollar bill and cut it up into a trillion pieces, one of those pieces would be a picogram, and then if you take that piece and then take off about less than a third of it, then that would be this, 0.26, about 0.3 picograms. Do you think you could see it? No. It wouldn't be visible. So a billion water molecules you wouldn't be able to see. And this would be how many liters? This would be picoliters. You know, we assume water is about 1 gram per milliliter. So milliliters, I mean. So anyway, it's being extremely small, difficult to see. All right, so the big advantage of defining a mole this way is that. Okay, we just did that conversion. So this brings us to something called stoichiometry. Stoichiometry is a quantity relationship. So we relate one thing to another. This is just a generic map. This is a stoichiometry map. This is a very common map. And so what we just did was we took the quantity in number of particles and converted that to moles using Avogadro's number. This is the abbreviation for Avogadro's number, N sub A. So we took the quantity and then converted it to mole using Avogadro's number here. And we got moles. And so this is where we are in the map. And then we took the moles and then converted it into mass in grams. So we took the moles and then used what we call the molar mass here. The molar mass is how much this mole of this stuff weigh. And then we got the grams. And then we converted it into picograms. So this is stoichiometry here, and it's just relating different quantities. Quantity in mass, quantity in moles, quantity in number. Stoichiometry is just using dimensional analysis in this one. So there's some other calculations here. Actually, we'll take a look at this one. Here we're going to go the stoichiometry map in the other direction. How many molecules are in 454 grams of water? 454 grams is about a pound of water. And so a pound of water, which is about 454 grams, has how many molecules of H2O? And so in the stoichiometry map, we're going to have two important conversion factors. One is the molar mass. The molar mass tells us how much a mole weighs. So if we have 454 grams of H2O, then I have two masses for H2O. I have the molecular mass. Did I already write that on the board, right? And the molar mass. And so H2O is 18.02. If I go and say 18.02 U per molecule, we call this the molecular mass. That's the molecular mass. However, if I say 18.02 grams per mole of molecules, then we call this the molar mass, how much a mole of it weighs. Molecular mass and molar mass are often confused, but they're two different things. So over here, I'm going to use the molar mass, 1 mole of water molecules. Now, the abbreviation for mole is not so different. You know, a mole is MOLE, the abbreviation for mole is MOL. So we just say one letter. And so I'll just say 1 mole, MOL, of water molecules weighs 18.02 grams. And so the grams of water cancel, that leaves us with moles of water, and then I'm going to use Avogadro's number. 6.022 times 10 to the 23rd H2O molecules per mole of H2O molecules. And so moles of H2O molecules cancel, and then we'll calculate it. So this, we can see 454 grams of water is 454 milliliters. That's a lot of water. It's almost 500 milliliters. And so we can easily see that. 454 divided by 18.02 times 6.022 times 10 to the 23rd. So a pound of water is going to have 1.51. How many sig figs are we allowed? 3. So I'm going to carry one extra. 1.517 times 10 to the 25th H2O molecules. And so what is that? That's 1.517 times. I'm going to break it down into a trillion. Or a trillion is how many? 10 to the 12 is a trillion, right? And then I'll do another trillion. So that's a trillion trillion. That's another 10 to the 12. And then I got to do times 10. That'll give me 10 to the 25th. So I'm going to multiply this by 10. This is going to be 15.17 times 10 to the 12 times 10 to the 12 H2O molecules. And so in other words, rounding this off, this comes out to 15.2 trillion H2O molecules. And so we can easily see 15.2 trillion water molecules. That would be equivalent to about a pound of water. About 454 milliliters.
Why did you multiply by 12?
I need to get 10 to the 20. There's no metric. Is there a metric prefix or 10 to the 25th? No. And so I didn't want to write in scientific notation. I just wanted it to, 10 to the 25th is a hard number to grasp. And so what I did was I converted 10 to the 25th into 10 to the 12 times 10 to the 12 times 10 to the 1st. And so that adds up 12 plus 12 plus 1 gives us 25. And 10 to the 12th is a trillion, so we know that. That's a trillion, and then 10. So I moved the decimal over 1. The 15.2 trillion. Trillion is a little bit more.
Would that first answer though be acceptable? Like on a
Yeah. This is fine. This is the answer. In fact, that's what they got. They got 1.52 times 10 to the 25 molecules of water. Okay, the next thing we're going to look at is percent by mass composition. And there are different ways of expressing composition. So 7.6 is percent composition. An example here is, let's look at H2O. What's the percent composition of H2O in terms of hydrogen? What percent hydrogen is H2O?
232.
Yeah, 2/3%. And so over here, I see that if I look at the percent hydrogen, this is going to be by atom or mole or dozen, but we don't do dozen. You know, if I have a dozen, dozen's still too small to see. So if I look at one single molecule of this, then I need to know how many hydrogen atoms. I'm going to have 2 H atoms over a total of how many atoms? A total of 3 atoms total. Times 100%. So this is going to give me 67%, let's say. Just round it. I can be more exact. I'm allowed more sig figs, but we'll just go with 67%. So this is 67% hydrogen. What's the percent oxygen? Well, if it's 67% oxygen, it's going to be 67% hydrogen by mass, or no, by atom. And then there's going to be 33% oxygen by atom. Now you might think, well, shouldn't we call this H2 and O2? And the situation is no, we don't call it H2 and we don't call it O2, we just call it H. Because the H's aren't even connected to one another. You know, they're split apart by this oxygen. And so when we look at the structure of water, it's these 2 hydrogen atoms and an oxygen atom. If I wrote H2 here, that would imply I have hydrogen gas in water, but there's no hydrogen gas in water. It's just H. And the same thing here. This is by atom or by mole. So if I had a mole, you know, this would be 2 moles of hydrogen, 3 moles total of atoms. So we get the same percentage. It's by atom or mole. Atom or mole. I should say or, no. Mole. Moles of atoms. That's a percent composition, but we can also do percent composition by mass. And so we'll go look at H2O, and this time we're going to do percent by mass composition. And so if I want the percent hydrogen by mass, then I need to know how many grams of hydrogen over how many grams total, or U, times 100%. Well, I know how much hydrogen I have. I mean, when I look at H2O, H2O has 2 hydrogens, and those 2 hydrogens, that's 2 times 101 is going to give me 2O2. And then I have 1 oxygen, and that's going to be 16.00, which is going to give me 16.00, and this is going to give me 18.02. And so in 18.02 total water molecules, I'm going to have 2.02 grams of hydrogen in 18.02 grams of H2O times 100%. This mass is perfectly fine for this calculation, but for this calculation, I'm going to end up with 3 sig figs. And so it's okay here, but when I calculate the grams of hydrogen, I'm going to calculate it using the other one. Because here I don't want 3 sig figs, I want 4 sig figs. And so rather than calculating it like this, what I'm going to do here is I'm going to go 2 times 1.008. If I use 1.008 instead of 1.01, then I'm going to get here 2.016. If I have 2.016 grams of hydrogen, that's going to give me 4 sig figs here in the division. And so this is the case. Over here it's perfectly fine because all I need is 2 decimal places. Over here it's not fine because I need 4 sig figs. 4 sig figs will carry out as 4 sig figs here. And let's calculate the mass percent hydrogen. And so this is going to be 2.016 divided by 18.02 times 100. And so I get 11.18, and I'm going to carry 1 extra digit. So this is going to come out 11.18 sub 7% hydrogen. If water is 11.187% hydrogen, then the percent oxygen we can calculate because they have to add up to 100. And so the percent oxygen by mass has to be 100 minus that, which is going to be 88.813% oxygen.
How do we know how many sig figs we need?
Usually we need 4.
But your initial calculation, you used 1.01, right?
Yeah.
So you don't need to change that.
I'm not going to change that. I could change it to 2.016.
Wouldn't that throw off the calculation on the other side then?
Yeah, it's going to throw off this calculation a little bit. So I could put this as 18.016, but there's a trade-off. The trade-off is speed versus accuracy. Yeah. So sometimes we lose a little bit of accuracy by increasing the speed. And so if I put this as 2016, then it's harder to add up in more complex molecules. And so if we go 2 decimal places, it's very quick because you usually can do these in your head. And so if somebody asks me the molar mass of ammonium nitrate, it's very easy. I can do that in my head because I have 2 nitrogens, that's 2802, 4 hydrogens is 404, and 3 oxygens is 648. And so I just add that up in my head. Versus if I start adding more and more decimal places, then it's harder and harder to add it up in your head. That's all. And so this is the speed versus accuracy. Over here, though, we want to do to 4 sig figs. We want 4 sig figs, so that's okay. There, it will throw it off a little bit, but we'll live with that.
So you said, so as far as the exam, which would be the proper way to do it? Because if we were to add the 6 to it, it would change our indefinite answer, wouldn't it?
You could do it. For example, here, if I did 4 sig figs 1008, we'll change this to 2.016, which would change this to 18.016, which would change this to 18.016. You could do it that way, that's fine. But the situation is, if you do it to 3 sig figs, and you could have easily done it to 4 sig figs, it's better to have it to 4 sig figs than 3 sig figs. The more sig figs, the better. You know? And so some people will weigh it out, they'll weigh it out to 2 sig figs, or measure it out to 15 milliliters. Some people will do 3 sig figs, 14.9 milliliters. I'd rather have the 14.9 than somebody round it up to 15. So when we look at the composition, this would result in kind of an odd composition of water. In terms of the composition of water here, it would be, what would it be? 11.19 maybe. 11.19 parts of hydrogen. And how many parts of oxygen? 88.81 parts of oxygen. And so we have 11.19 parts of hydrogen, 88.81 parts of oxygen by mass. And so this would be the formula by mass. when we look at the formula by mass, that doesn't make it easily to visualize. Is it easy to visualize? And the other thing is, when we look at the atoms, there's more hydrogen atoms, but when we look at the masses, it's flipped. There's more oxygen. There's more oxygen because oxygens are 16 times heavier than hydrogen. So this is why there's a lot more oxygen here when we do it by mass. But when we do it by atom, there's a lot more hydrogen by atom. But a hydrogen atom doesn't weigh much. And so this is what we get. Oftentimes we want to know by mass. We don't want to know by atom, because if you buy a pound of fertilizer, how much nitrogen are you getting? So ammonium nitrate, we can figure out the percentage of nitrogen in here by atom or by mole. The percent nitrogen here is, we have 2 moles of nitrogen. And how many moles of atoms do we have? It's 1 plus 4 is 5, plus 4 is 9. So 9 moles of atoms times 100%. So there are a total of 9 atoms in there. And so when we look at this, ammonium nitrate has how much nitrogen? It's 2 divided by 9. 22.22% nitrogen. By mole or by atom? Well, this is moles, so let's just do by mole. Yeah. But when you go by a pound of nitrogen, that's not very helpful. So if we were to go by a pound or a kilogram of nitrogen, how much nitrogen are we getting? And so here, what we're going to do this by mass. We already calculated the mass of ammonium nitrate. And so we'll look at the percent nitrogen by mass. The percent of nitrogen by mass is how many grams of nitrogen do I have? So I have 2 times 14.01 grams of nitrogen. So that would be 28.02 grams. This is 2 moles. That's how many grams per mole. So we get 28.02. Over the total was 80. What was the total? Again, 80.06 grams total. And so if I do this, 28.02 divided by 80.06 times 100, and I get 34.99, allow 4 sig figs, so I'll carry 1 extra. 34.988% nitrogen by mass. And so in other words, when we round this is going to round to 35.00% nitrogen by mass. So if I had 100 grams of ammonium nitrate, I'm going to get 35 grams of nitrogen on that. So let's buy a kilogram, or about 2 pounds of ammonium nitrate. How many grams of nitrogen will I get? So, let's see. 2 kilograms of ammonium nitrate. How many grams of nitrogen am I going to get? So there are 2 ways to solve this. One, calculate the percent nitrogen by mass, then use as a conversion factor, then use as a conversion factor, CF. Well, we already calculated the percent nitrogen by mass in here, and now we're going to use it as a conversion factor. And so if we have 1 kilogram of ammonium nitrate, then the conversion is 35%. So that means there's 35.00 out of 100. In the units, we can use whatever units we want. So it's 35, as long as they're mass units. So it's 35 kilograms of nitrogen per 100 kilograms of ammonium nitrate. Which is going to give us 0.35 kilograms. And then we're going to times that by 1,000 grams per kilogram. And so this is going to give us 350 grams of nitrogen.
Professor,
Mhm.
is that still NH4NO3? I can't really tell when you wrote at the top.
This one?
No. Right.
This one?
No, the one to the left of where you're pointing. The 1HG, it's 4, right?
Yeah.
Okay. Sorry, I couldn't read that.
No, I made a mistake. It should be NH4. Okay, that's one way. The other way of doing this is by using dimensional analysis, D8. So if I use dimensional analysis, I'd start off with 2 kilograms of ammonium nitrate. And then I just convert this to grams. So I'd go 1,000 grams per kilogram. And that gives me grams of ammonium nitrate. Well, if I have grams of ammonium nitrate, then I can convert it to moles. That's part of the stoichiometry map. And 1 mole of ammonium nitrate weighs 80.06 grams. And so the grams of ammonium nitrate cancel, and that leaves me with moles of ammonium nitrate. Once I have moles of ammonium nitrate, then I know. Like, for example, if I had 1 dozen ammonium nitrates, then I have 2 dozen nitrogen. So if I have 1 mole of ammonium nitrate, then I have 2 moles of nitrogen. So 1 mole of ammonium nitrate contains 2 moles of nitrogen atoms. This is not N2 gas, it's nitrogen atoms. And so the moles of ammonium nitrate cancel, and that leaves us with moles of nitrogen atoms. And then I know how much nitrogen weighs. It's 14.01 grams on average per mole. And so the moles of nitrogen cancel, and that leaves us with grams of nitrogen. And so this is going to come out to 350 grams of nitrogen. Here, we get the same thing. In the second case, I didn't bother calculating the percent composition of mass. I don't need it. Yeah. In the first case, I did. Mm-hmm.
Where did you get 2 moles of nitrogen and 1 mole of
If I had 1 ammonium nitrate, how many nitrogens are there? There's 1, 2. If I had a dozen ammonium nitrates, then I'd have 2 dozen nitrogens. If I had a mole of ammonium nitrates, then I have 2 moles of nitrogen. So it's just the ratio. That's where I got it from. So the formula is very important because the formula is going to tell us the composition. And we can get some clues as to the properties of this. But how do we get the formulas themselves? Like, for example, where do the formulas come from? And so let's look at the next section here. We'll look at some more sample calculations here. The formula is very important because it's going to tell us clues as to the reactivity and the property of these things. And so how do we determine formulas? So determining formulas, we typically take an unknown substance, unknown pure substance, and we want to know what it's made out of. And so if we have some sample of unknown pure substance, then what we do is we send it out for analysis. This is chemical or elemental analysis. It usually costs money. And so you send out a sample, you pay them, and what they do is they determine what elements are present. So there are two ways that this is reported. One, they'll give you grams of each element present. And so you send out the gram sample, let's say you send out a 5-gram sample, and then they'll analyze it. They'll tell you, out of those 5 grams, you have 3 grams of carbon. You have 1 gram of this, you have this amount. Or 2, they'll give you the percent of each element present. And this is percent not by mole, this is percent by mass. A formula is not a mass ratio. You know, like the mass ratio for water is H11O89. That's not very useful. And so what we're going to do is we're going to convert the mass ratios here into mole ratios. And so we want to convert to moles. And then get the simplest mole ratio. Sometimes we have to do 2 steps to get there. Sometimes we can do 1 step to get there. So let's do an example of this here. So 59, a researcher exposed 11.89 grams of iron. This is a little bit different. Let's do 60 here. 60, a compound is found to contain 39.12% carbon. So you sent out this compound for chemical analysis, and then you got a report. The report is percent of each element present. And so we have this unknown compound. This unknown compound is carbon, 39.12% by mass. Hydrogen, 8.772%. Oxygen, 52.11%. The first thing we look for is, does this add up to 100%? And this adds up to 100.02%. 100.02%, how can we have more stuff in there than is in there? Yeah, probably rounding and sig figs. So this is close. And so it's just round off error. Rounding issue. So that's why we're getting more than 100%. Okay, but we don't want a mass ratio. Because if I have a mass ratio, C 39.12, H 8.772, O 52.11, what would we do with that? Maybe we'd round it, C 39, H 9, O 52. Is that very useful? It's not very useful. This is not useful. So formulas are not mass ratios. Formulas are mole ratios. So what we're going to do, the whole goal of this is to get the mole ratio. To get the mole ratios, we need to do a mass to mole conversion. So the first step here is we're going to assume 100 grams. If we have 100 grams, then what that means is this is going to be 39.12 grams of carbon, 8.772 grams of hydrogen, and 52.11 grams of oxygen. Okay, again, that's still just the mass ratio. That's not what we want. We want the mole ratio. So what we're going to do here in stoichiometry is called the gram to mole conversion. Gram to mole conversions are very common. So we'll take the grams here and convert it to moles. 1 mole of carbon atoms on average weighs 12.01 grams. And so we can get the moles of carbon atom. So 39.12 divided by 12.01. And so we got 3.257. We're about 4 sig figs, so I'm going to carry 1 extra. 2 moles of carbon. Hydrogen, here, should I use 101 or 108? So 1 mole of hydrogen weighs 10. Yeah, I should use 108 because that will retain 4 sig figs. Here. And so I'm going to do 8.772 divided by 1.008. And that's going to give me 8.702, so 3 moles of hydrogen. And then we'll do oxygen. 1 mole of oxygen weighs 16.00 grams. And so 52.11 divided by 16 gives me 3.256 of 8 moles of oxygen. Now, formula is a mole ratio. So now we have the mole ratio. So it's going to be carbon, 3.2572, hydrogen, 8.7023, oxygen, 3.2568. Does that look good to you? No, this doesn't look so good. Maybe we could round it, because it should be simplest whole number ratio, right? So we could call it carbon 3, hydrogen 9, oxygen 3. Does that look okay to you? Well, it's a bit too much rounding. I mean, this is 3 1/4. That's 8.7. It's a bit too much rounding. And so to clean this up, we divide it by the smallest number of moles. When we divide it by the smallest number of moles, which one's smallest? It looks like this one's smallest. So we'll go 3.2572 divided by the smallest number, which would be 3.2568. We'll take hydrogen. It's going to be 8.7023 divided by the smallest, 3.2568. And then oxygen will be 3.2568 divided by 3.2568. So let's see what that gives us. So I'm going to do 3.2572, 3.2572 divided by 3.2568 gives me carbon 1.0001. Okay, hydrogen is going to be 8.7023 divided by 3.2568. Hydrogen comes out to 2.6720. And then oxygen is just going to come out to 1.0000. Okay, now should I round this? Should I round it to carbon 1, hydrogen 3, oxygen 1? I don't feel comfortable rounding 2.6 to 3, do you? I mean, that's a pretty big rounding step there. And so what we need to know is this. If we have x 0.5, then what we should do is double everything. If we have x 0.33, then what we should do is triple everything. If we have x 0.67, we should triple everything. The reason I want to triple it is because this is 2 2/3. Do you see that? This is about 2 2/3. In other words, this is equal to 2 2/3. Because 2/3 is about 0.67. In other words, well, 2 is, this would be 6/3 plus 2/3, which gives us 8/3. And so this is why I want to triple it. I want to get rid of the thirds. And so if I triple everything, this is what I'm going to end up with. I'm going to end up with C3.0003 H. Okay, so I'm going to take 2.672 and multiply by 3 times 3. And that's going to give me 8.01603.000. Okay, now I feel much more comfortable rounding this. Because when I round this, I'm going to round this to C3H8O3. So here, I'm just rounding this down to 8, which is reasonable. Whereas here, I feel a little uncomfortable rounding that up to 9. And so C3H8O3, this is what we call the empirical formula. The empirical formula is the simplest whole number ratio. And unfortunately, are we out of time then? Yeah, we're out of time. So I was going to have you do the next one. So when we come back, you're going to do this next calculation here.